Today we are going to learn how to measure the enthalpy change. In the last session, we discussed about some enthalpies, right, and their bond energy diagrams. Now we will learn that how can we measure the enthalpy change. There's a technique which is very important in your syllabus. We measure the enthalpy change of some reaction by a technique which is called calorimetry. Calorimetry. So we have an instrument which is called, we have a device which is called as calorimeter. So we perform our experiment in this calorimeter. The procedure is not there in the syllabus. You just have to remember that in calorimeter we use known amounts of reactants and known volumes of liquid. Then we also measure the temperature change of the liquid in the calorimeter as the reaction occurs. Okay, what we take known amount of reactant and known volume of liquid. Then it shows changes in temperature. We measure that changes in temperature which happens in the calorimeter as the reaction occurs. So in calorimetry technique, it is based on the fact that it takes 4.18 joules of energy to increase the temperature of 1 gram of water by 1 degree Celsius. So it is a fact that if you have to raise the temperature of 1 gram of water by 1 degree Celsius, it takes how much amount of energy? 4.18 joules. And this is nothing, this is called your specific heat capacity or small c. We represent it by a small c of the liquid. So what is specific heat capacity of the liquid? The energy which is required to raise the temperature of 1 gram of substance by 1 degree Celsius or 1 Kelvin, which is called the specific heat capacity. So for water it is 4.18 joules per gram per degree Celsius. Okay, 4.18 is the energy per gram. That means 1 gram of the substance, and degree Celsius means it raises the temperature by 1 degree Celsius. Is it clear? Clear? Any doubt?
Yeah, it's clear.
Write it down.
No.
There's a formula Q is equal to MC delta T, which you have to use in the numericals, where Q is the heat transfer in joules, okay, in the calorimeter. M is the mass of water in grams. T is specific heat capacity in joules per gram per degree Celsius. If it is not given, you will take it the 4.18. Delta T is the change in temperature in degree Celsius. So as 1 centimeter cube of water, it weighs 1 gram, right? That's why density is 1. We can substitute volume of water in centimeter cube of water for mass of water in gram in this. Okay, so it comes out to be in joules per gram per degree Celsius because density of water is 1. Okay, so write it down. Formula is important. You have to calculate the energy transport. All the values are given to you, so you can easily substitute and can answer.
I'm done.
Here, good question for today. That propanol is a liquid and it has the structure S. The equation for the complete combustion for propanol is given. Then you have to use the following bond energies. It is given to calculate a value for the standard enthalpy change of the reaction. I hope you remember bond energy value is, if you want to calculate the enthalpy, standard enthalpy change, and what you have to use, summation of bond energies of reactants minus of summation of bond energy of products. Explain why it would be more accurate to use the exact bond energies rather than average bond energies in this calculation. So I told you the concept of bond energy and exact bond energy. That way, that you have to write it. This for 1 mark. Done?
Yes.
So So we have studied Q is equal to mc delta T, right? This is our equation. But a rise in temperature is given a positive sign. So if you have to calculate the value of delta H, it is negative for exothermic reaction, and a fall in temperature is given a negative sign. So the value of delta H is positive for an endothermic reaction. Okay, for exothermic reaction, temperature is positive, so a delta H is negative. And for endothermic reaction, your fall in temperature is given a negative sign, so the value of delta H is positive. Because enthalpy is what? It is also the heat, right? Heat absorbed at constant pressure. Write it down.
Done.
The energy released in calorimetry experiments for a known number of moles of a specified reactant. Why known number of moles? Because we are putting in it the known amount of reactant. So it is given by Q is equal to mc delta T. When we multiply this up to 1 mole of a stated product or reactant, so equation is delta H is equal to minus mc delta T, and the negative sign shows that the reaction is exothermic. So solve this question. Calculate the energy transport when the temperature of 25 centimeter cube of water rises from 23 degrees Celsius to 54 degrees Celsius. Calculate it and tell me the answer. This 75 centimeter cube is volume. So you have to calculate the value of mass. Density of water is 1 gram per cent.
The answer is 9,718.5.
What?
9,718.5.
Calculated it using the formula Q is equal to mc delta T. What is the value of M
Yeah.
you have substituted?
75.
75 grams. And value of C is
4.18.
and the value of delta T is
31.
let me figure it out.
Hey students! Interested in boosting your studies? Enroll now at Keddy Edtech. We offer online tuition for the Cambridge curriculum, grades 6 to IGCSE, AS, and A-level. Start learning with us today.
Very good. Next law is Hess law. What is Hess law? It is very simple. It just states that the total enthalpy change in a chemical reaction, total delta H in a chemical reaction, it is independent of the route by which the chemical reaction takes place as long as the initial and final conditions are same. Okay, that means it simply means that the delta H it only depends on initial stage and final stage. It does not depend on the route it has taken. It doesn't depend on the path. So it is independent of the path in which the chemical reaction has taken place. Many chemical reactions occur in 1 step, 2 step, 3 step. So it doesn't depend on that path. It just depends on the initial state of the substance and the final state of the substance. So it is your state function. Write it down.
I'm done.
For example, enthalpy change is the same no matter which route is followed. So it is the direct route A plus B, it gives you C, it is the direct route. Enthalpy change is same here also. And in indirect route, first it converted into F plus G, then into C. So the enthalpy change, for example, if it is delta H1 and if it is delta H2, so it means delta H is equal to delta H1 plus delta H2. The enthalpy change is same. Similarly, in direct route 2, here also the enthalpy range changes same. Right?
I'm done.
We can use Hess law to calculate the enthalpy changes that cannot be found by experiments using calorimetry. Okay? So we calculate enthalpy changes by calorimetry also, by the Hess law also. For example, the enthalpy of change of formation of propane, it cannot be found out by experiment. Why? Because hydrogen gas, it does not react with carbon under the standard condition. So we cannot calculate it with the calorimeter. We have to use the Hess law to calculate the enthalpy change of formation of propane, where carbon in its standard state reacts with hydrogen. Okay, and hydrogen in its standard state is a gas. So hydrogen does not react with carbon under the standard condition. Write it down.
I'm done.
So there you can see the enthalpy cycle or energy cycle for calculating the enthalpy change of a reaction. This dashed line, it shows the indirect process or two-step process. What happens? The direct route is this is your elements, okay, and this is reactants and this is products. So the enthalpy change of a reaction is reactant to products. Okay. So what happens here? The direct route, when you have to calculate the enthalpy change of a reaction, so the formula to calculate it is delta H2 minus delta H1, where delta H2 is enthalpy change of formation of two products from the elements in the standard state, and delta H1 is the enthalpy change of formation of reactant from their elements in a standard state. Okay, so here you can match that the direct route enthalpy in elements to products without going into reactant, it is equal to your indirect route. This dashed line represents indirect route. That means delta H2 is equal to delta H1 plus delta HR. Okay, so from this you can calculate the value of delta HR, which comes out to be delta H2 minus delta H1. So write this down and we'll do a numerical.
I'm done.
Okay, so this is a question. From this question, you can understand the application of Hess law. Calculate the standard enthalpy change for the reaction. This is your reaction. Enthalpy changes of formation are given to you. I think now you know what is the difference between enthalpy change of reaction and the enthalpy of formation. So write this question down. Can you? This is the Hess law diagram. So here you can see that these are your elements. It is your reactant, it is your product. So use the formula, solve it, and tell me the answer. The enthalpy of formation means 1 mole of the compound is formed from its elements in the standard state. So let me tell you the steps first. You have to solve it on your own. You have to apply Hess law. Okay, delta HR is equal to, that means direct route is equal to indirect route. So you have to apply the formula. Then you have to insert the values of delta H by taking care to multiply by the correct number of routes. Then you have to rearrange the figures to make your delta HR the subject, that means the left hand side. Now there are two things which you have to know. You will solve it, I know, but the two things you have to remember is that here the enthalpy of formation of NaHCO3 you have to multiply by 2, because 2 moles are there in the equation. While we have studied that in enthalpy of formation only 1 mole of compound is formed, but here 2 moles of compound are forming, so you have to multiply it by values of this sodium carbonate, CO2 and H2O, they're added together to give delta H. So you have to take care of the sign. Try to do it.
I got plus 91.5.
See? You are saying something?
I said my final answer was plus 91.5.
That's 91.6, right?
I got 5, not 6.
Okay, so this answer is correct. 91.6 or 91.5 is okay. So you understood the question, or there's any doubt?
I understood the question.
So yes, so we have completed the chapter. You have to remember only two things when doing enthalpy change or energy cycle. You have to remember that enthalpy change of an element in its normal state is 0, and you must take into account number of moles of reactants and products in each part of the energy cycle. Okay, you have to remember enthalpy change of an element in its normal state is 0. So take a screenshot of your homework question. This one is your homework question. Take a screenshot. You have to make the structure first and then use these enthalpies after counting the number of.
Okay.
So what we have studied in this chapter is that exothermic enthalpy changes have negative delta H values and endothermic enthalpy changes have positive delta H values. Then we have studied one formula that enthalpy change you can calculate by Hess law also, by calorimetric technique also. Formula is Q is equal to MC delta T. Okay, for 1 mole it is equal to delta H is equal to minus MC delta T. Definitions are important. For standard enthalpy change of formation is enthalpy change when 1 mole of compound is formed from its elements under the standard conditions. Okay. Then Hess law, we use Hess law to calculate enthalpy changes which do not occur directly or which cannot be found out by experiment. Bond breaking is endothermic process. You should supply energy, and in bond making, energy is released, so it is exothermic. Concept of average bond energy is also important. It is used because the strength of bond between two particular types of atom